This leads us into the idea of half-life. Half-life is more than just a really cool arcade game. But anyway, I digress. I used to play this game called Half-Life. Anyway, half-life in science is the time it takes for half of a sample to disappear, all right? And so if you start with 1 mole of substance, the half-life is literally the time required to get down to only half of a mole. Now on the graph on the right there, this is a hydrogen peroxide decomposition. You're starting with 0.020 moles per liter, and the first half-life occurs when you get down to half that value, or in this case, 0.010 moles per liter. So you can see there, if you go down to the dotted line, that took 654 minutes to go from 0.020 to 0.010. So for this reaction, the half-life is 654 minutes. Once you know the half-life, then you can start figuring out quantities based on multiple half-lives. So what I mean by that is that 2 half-lives, all right, you would use twice the half-life time. So 654 times 2, 1,308 minutes. So it's going to take 1,308 minutes to go to 2 half-lives. You went from 0.020 to 0.010 to 0.0050 moles per liter. And you can see how there's this 654 interval between the different half-lives. So at 4 half-lives, you're at 2,616 minutes, etc., etc. In half-life analysis, you really never go to 0. All right, you never go to 0 concentration, moles per liter. And because we're dealing with 10 to the 23rd of these crazy molecules or atoms at one time, that's usually pretty reasonable. There are some exceptions, like sodium metal and water is incredibly product favored, but more often than not, you get down to a very, very small quantity of the original stuff where it's basically considered reacted, and that's up for you as the scientist to decide when it really has all reacted or not. H2O2 decomposing to water and O2 is first order, all right? And so we're starting here with 0.020 moles per liter H2O2. After 1 half-life, which we saw in that previous slide was 654 minutes, we're down to half the original quantity. So that would be 0.0100 moles per liter. So knowing about half-lives, you can see then how long it takes. Notice that you're down to half of the original reactant concentration. After 2 half-lives, or 654 times 2, which is 1,308 minutes, you've now gone down to 1/4 of your original concentration. So 0.020 to 0.010 to 0.0050 moles per liter. So you can see this kind of curve that happens, and that's very, very common. If you go 1 more half-life, now you're at 1,962 minutes. You're at 3 half-lives. That's 1/8 of the original reactant, which is still around. Why stop there? 4 half-lives would be that 654 times 4, or 2,616 minutes. You can see that you're now down to 0.00125 molar. That's 1/16 of the original concentration. So half-life has some uses for it, but it's also interesting because you might at first think that, oh, these reactants will go automatically to 0. Well, not usually, and that's something we're going to start to explore both in this chapter and in Chem 223. Here's an example with how half-life can be really useful. Sugar fermenting, like all biology things, is a first-order process, and there's an enzyme being used as a catalyst. Enzymes are nature's catalysts. Our bodies have lots of them working around inside us right now. Pretty cool. But anyway, sugar plus the enzyme goes to some kind of products. We don't have to care about the products. Anyway, it's a first-order process, so rate equals K times the concentration of sugar to the first power. To the first power is usually ignored, so just sugar. Rate constant K, 3.3 times 10 to the minus 4 inverse seconds. Question is, what is the half-life of this reaction? Oh, geez. If you are familiar with video games, this is the picture of Half-Life, the game I used to play a lot. Half-Life 2, I know. I really need to grow up as your instructor, but anyway, I couldn't resist throwing it in. Gordon Freeman is the name of the dude there in the glasses. He's really cool. But again, that really has nothing to do with chemistry. My apologies. In the problem, going back to your regular scheduled programming, rate equals K times sugar, and K equals 3.3 times 10 to the minus 4. 4, what's the half-life of this reaction? Now, this is kind of cool. If you're at a half-life, then R over R0, i.e. the amount you have left divided by the amount you started with, is going to equal 1/2. So if you started with 1 mole, you'd be at half a mole, and half divided by 1 is 1/2. But you could do it for any number. You started at 0.2 moles and you have 0.1 mole left, that would be a half-life, that would be 1/2. So regardless of where you are, R over R0 will equal 1/2 when the time equals half-life. T1/2 is the symbol for half-life. So if you do a little math here, natural log R over R0 equals minus KT. Well, natural log of 1/2 is negative 0.693. So negative 0.693 equals minus K times T 1/2. Remember, we're at the half-life, so that's why our T is T 1/2 here, trying to show. Now, obviously, the negative signs will cancel, so we end up with a super handy expression to convert a rate constant K into half-life or a half-life into rate constant. Now for this problem, we're trying to find the half-life. So 0.693 divided by the rate constant K is going to give us the half-life. Now initially, the rate constant K is in inverse seconds, so our half-life is going to come out in seconds. So when you take 0.693 and divide it by 3.3 times 10 to the minus 4, you're going to get 2100 seconds to 2 sig figs. And if you convert seconds into minutes by dividing by 60 seconds per minute, you're going to get 35 minutes. So 35 minutes is the half-life for this reaction of sugar decomposing. T1/2 equals 0.693 divided by K is going to be super helpful to us. So make a note of it. It's a nice way to go from half-life to rate constant or rate constant K to half-life. This process only works for first order, but there are some second order and zero order equivalents to this equation. I'll show you them here in a little bit. So here's a given first order reaction, and K equals 0.347 inverse hours. And the question is, what is the half-life of this reaction? Okay, answer E is totally silly. Dr. Gordon Freeman was the hero of that half-life game. My apologies again for the bad references in the media. But anyway, the important part here, half-life equals 0.693 divided by K. So what I would do in this problem is take 0.693 and divide it by 0.347, and that's going to get us an answer in hours. Remember that K and T have to be the initial amounts. So T1/2 initially will be a value in hours. And from hours, I have to convert it to make sense of the answers. I have to convert hours into minutes. So I'm going to need to multiply by 60. So if you do the math, 0.693 divided by 0.347, it comes out to be 2.00, but it's 2.00 hours because K was in inverse hours. So 2 hours times 60 minutes per hour, 120 minutes. The next kind of problem is one that you'll see sometimes in classes like this, and there are two methods to determine the answer. And one way I'm going to refer to as the Chem 104 method, because in Chemistry 104, this is the way we actually tell students to solve it. But the better answer is to use that integrated first order rate law. So without further ado, we're back to the example, rate equals K times the sugar, K 3.3 times 10 to the minus 4, and we saw that the half-life is 35 minutes. So let's say that we start now with 10 grams of the sugar. We want to know how much is left after 2 hours and 20 minutes. Okay, no problem. And remember, half-life 0.693 divided by K. Well, in Chem 104, what we would do is we'd try and figure out the time elapsed, and the time elapsed will be equal to some integral of 35 minutes. So 35 times 1, 35 times 2, something like that. If you figure out 2 hours is 120 minutes, 120 plus 20, 140. 140 minutes divided by 35 is 4. So that means 4 half-lives have passed in this problem. So after 1 half-life, you're down to half the quantity, which would be 5 grams, and that would be 35 minutes. And then 2 half-lives, 70 minutes, you'd be down to 2.50 grams. third half-life, fourth half-life, you're at 140 minutes, 0.625. 0.625 grams is the answer. And this way it's awesome if your time elapsed is a whole number equal of half-lives, all right, like exactly 4. If you have like 3.65 half-lives, then it doesn't work quite as well. So the Chem 222 method, which is what I recommend highly for this class, is you go back to that first order integrated rate law. Now, because K is in inverse seconds, we need to convert our time into seconds. Seconds and K have to be the same kind of units. So you'd have to convert 2 hours into minutes first, 140, and then 140 minutes times 60, that's 8,400 seconds. Then natural log R over R0 equals minus KT. K and T are both the same kind of unit, seconds. R0 is 10 grams. R is going to be an answer in grams. And if you solve for it, and got to take the anti-log once again, stuff like that, make sure you know how to do these kind of problems. If you aren't, let me know. I'll help you out. 0.625 grams. So same answer. Now, really, in this class, I recommend the Chem 222 method because it may look weird, but honestly, it will get you out of any situation. And some of these problems will be much more difficult using the quote-unquote Chem 104 method because you may not have exactly like 4 half-lives. You might have like 4.17 half-lives or something. Now, the Chem 222 integrated first order rate law works great in all of them. Half-life is super useful for radioactive decay. And we talked about earlier how all biological processes are first order and most chemistry processes are first order. I would argue that all radioactive decay is a first order process as well. So this is an example with tritium. Tritium is radioactive hydrogen. It's a very small component of all the hydrogen around us. But anyway, it breaks down into an electron and a helium-3 isotope. The half-life, 12.3 years. So let's say we have 1.50 milligrams of tritium. How much is left after 49.2 years? And again, the half-life, 12.3 years. Electrons in this case are actually referred to as beta particles. And we're going to talk about that more in the next chapter of Chem 222. But for right now, we're focused here more on half-life and how we can use half-life to solve equations like this. What I would do, go back to the first order integrated rate law. Natural log R over R0 equals minus KT. We know R0, how much we started with, 1.50 milligrams. The time elapsed, 49.2 years, all right? But we're in a problem because we're trying to find how much is left, which is R, and we don't have K, all right? But since we have half-life, if you remember, half-life equals 0.693 divided by K. Or in this problem, let's use K equals 0.693 divided by half-life. So in your calculator, 0.693 divided by 12.3, the half-life, that equals the rate constant, that holy grail of so many of these problems. And it's 0.0564 inverse years. Half-life was in years, so rate constant will come out to be inverse years. Well, now we can use this K value, throw it up there in the integrated first order rate law. Natural log R over 1.50 equals minus KT minus 0.0564 times 49.2. Now, initially, it comes out to be negative 2.77. You're going to take the anti-log of both sides in order to get the natural log R over R0 down to just R over R0, as we've seen before. That comes out to be 0.0627. And I do want to comment that the R over R0 is the fraction remaining. So of the R0 we had, that we started with, 1.50 milligrams, 0.0627 is literally the fraction of that amount that's going to be remaining. So if we take that number and we multiply it by the amount we started with, 1.50, we're going to be down to 0.094 milligrams of tritium. So you can see how we used half-life to find rate constant. We then plugged everything into the integrated first order rate law, natural log R over R0 equals minus KT, and solve for R, 0.094 milligrams is left. Here's a problem with radioactive copper-64. It's used apparently in copper-2 acetate to study Wilson's disease. But anyway, the half-life has a half-life of 12.70 hours. What fraction of the copper-2 acetate remains after 2 days? Now, first of all, I hope you're starting to see here that time has to be in the same kind of units. And we have hours and we have days, all right? So the first thing I would do here is I would probably convert 2.0 days into hours, 48 hours. That will allow us to use the half-life and the time elapsed in hours, same kind of unit. So the fraction remaining is the r over r0. So natural log r over r0 equals minus kt. T is going to be 2 days in hours, 48 hours. But we also need to take 0.693 divided by the half-life to find k. Then take the anti-natural log to get r over r0 by itself. So here's what it looks like. Natural log r over r0 equals minus kt. I turned 2 days into hours because the half-life was in hours. 0.693 divided by the half-life will give you the rate constant. I didn't even calculate it here. I just went ahead and plugged it right on in. So plug this all in, take the anti-natural log, e to the natural log to the x to get just the fraction 0.073. If you don't get that answer, you let me know. No problem. But you can see this is sometimes kind of useful for figuring this stuff out. When it comes to first order, half-life equals 0.693 divided by k. And 99% of the time, that's the one you're going to use in chemistry. If you do have a second order or a zero order reaction, the half-life looks somewhat similar, but you do need to worry about the initial concentration of the reactant, A0. So you have to know how much you started with, and it will affect your half-life. So half-life in zero and second order is a little bit different story. We're not going to focus too much on that in this class, but in future classes that may become important. But even if you had to in this class, just realize you do need that initial concentration of the reactant to solve for the half-life. Radioactive elements have half-lives all over the place. Some of them are super long and some of them are super short. So you can see there that uranium-238 breaks down into 234 thorium and some helium with a half-life of 4.5 times 10 to the 9th years. 10 to the 9th is like a billion, so that's 4.5 billion years. And that's just to get rid of half the uranium-238. So imagine how long things will take. Carbon-14 is involved with carbon dating, and they use the carbon dating half-life of 5,730 years to figure out the ages of a lot of historical documents and stuff like that. That's a number that pops up quite often, actually. Radioactive Iodine 131 has a half-life of about 8 days. Element 106, named after Glenn Seaborg, one of my heroes, 0.8 seconds for it to decompose. And one of the newer elements, rontgenium, after the Rontgen guy that did X-rays, 0.0015 seconds. That's the kind of stuff like if I said, hey, look at my sample of rontgenium in my hand, and I opened up my hand, it would all be gone. And first of all, I shouldn't have it in my hand because it's obviously radioactive. It's an alpha emitter. We'll see in the next chapter. But anyway, you can imagine that this stuff, man, it doesn't last that long. And these are some of the newer elements they're finding. Very, very short half-lives, which means you just don't have the element around that long to study it. Medicine also uses half-lives, and drugs will have a half-life in your body, and it depends on age and lots of different substances. One kind of silly thing, but a good example, is the half-life of caffeine, 3.5 hours in the body. So I think I am perpetually above the 3.5 hours half-life threshold because I drink so much coffee. But anyway, you get the idea. They can use this in medicine to see how long they're going to last.